All right, we are back, and I'm realizing that this next few sections I'm about to record are really, really short. I guess I saved the shortest sections for today because, you know, it's a Saturday, it's about 8 p.m., and I'm tired, I want to go home. I want to go play Destiny 2, really. But we're going to talk about projectile motion example, okay? Particles, in a way, act like projectiles, okay? You know, that's kind of cool that they do that, right? Because we can kind of, you know, flash back to when times were simpler in AP Physics 1. So first off, when a when a charge travels through a uniform electric field, it has two constant things. A constant force, and therefore, if it has a constant force, it must also have a constant acceleration. Okay? So if we have a particle that's entering a uniform electric field, okay, first off, we can tell, so these are like two plates, right? So, I guess I should read the problem first because it talks about it. It takes 3 × 10⁻16 joules of energy to accelerate a proton to 600 kilometers per second. Suppose such a proton was projected horizontally into a uniform electric field that exists between two plates as indicated by the shaded region. The proton moves 6 meters horizontally before striking one of the plates. Ignore gravity, okay? Draw plus and minus signs to indicate the charge on each plate and arrows in between to indicate the direction of the electric field in the shaded region. Okay, well, how do we know which plate's positive and which one's negative? Look at your battery, okay? We have positive right here on the bottom, and the positive is going to flow through the wire through the bottom, okay? The negative terminal is connected here, okay? And so the negative goes through there. So our positive plate is going to be the one on the bottom, okay? And then our negative plate is going to be the one on top. Okay? And therefore, if the positive plate's on the bottom and the negative's on the top, then the electric field should be going straight up. Okay? Okay. Draw the path the proton takes and describe the path. Well, what's going to happen is if the proton enters this field, it's going to follow the electric field because protons follow the electric field. Okay? So positive charges follow the electric field. So when it goes in, it's going to be affected by the electric field. It's going to have electric force applied by the field. So when it goes in, it's going to look kind of like this. It's going to go kind of straight for a bit, and then it's going to kind of, okay? Or I guess, I am so sorry. I should have drawn it a little bit longer than that, because it splats on the plate at 6 meters, okay? So that's more accurate to where it should land. It should land right at the 6, okay? Okay. Okay, we did the electric field. Okay, so the proton actually takes a parabolic path, okay? Even though it doesn't really look like it, it is parabolic, even though it's a really stretched parabolic path, okay? Okay, how much time elapses after the proton enters the field but before the proton strikes a plate? Well, the only thing that really... So what does it say? Does it tell us how long it takes? Well, we need to figure out how much time passes, right? Well, we know that if the projectile goes 6 meters horizontally and has a constant velocity, you know, there's no forces in the x direction affecting it, okay? Then we can figure out the time it's there based upon the distance it goes, right? So if we just take x equals vx0 times t, okay? Well, Vx0, it gives us is 600 kilometers per second, but we need to convert that to meters per second so that we need to convert that to meters per second. That would give us 600,000. Okay. So then we would do x is 6 meters equals 600,000, okay, times t. And now you're thinking like, wait a minute, that's a really, really fast speed. Like, to put that into perspective, this is insanely fast, right? So it only goes 6 meters, so the time's got to be really, really small. And we would calculate that out to be about t equals 1 times 10 to the -5 seconds. That is incredibly fast, okay? That is a really short amount of time, okay? Okay, what is the acceleration of the proton when it's in the electric field? Okay, well, the proton, okay, is going to be subject to acceleration. If we're ignoring gravity, like it says in the earlier part of the problem, ignore gravity, then the only acceleration is going to be upwards towards the plate because that's the net force, okay? The only net force is in the y direction from the electric fields, okay? So therefore, we would need to use our kinematic equation for the y direction, y equals 1/2 a sub y t squared, okay? We're going to use the t from earlier, okay? And then the y distance is given to us as 0.6 meters. So we're going to just plug all that stuff in. 0.6 equals 1/2 a sub y, which we don't know yet, and then t is 1 times 10 to the negative fifth, okay? Multiply by 2 on both sides, right? You get 1.2 equals a sub y times 1 times 10 to the negative fifth, and then divide by 1 times 10 to the negative fifth on both sides. And you're going to get this insane acceleration. That is 1.2 times 10 to the 10th meters per second squared, okay? That is an absolutely insane acceleration. Here's a fun fact for you, okay? If you look on the Physics C formula sheet, let's see if it's there. Should be on there, right? That is actually, so this is, if you were to go this acceleration for 1 second, you would be going 1.2 times 10 to the 10th meters per second, and that's actually faster than the speed of light. Speed of light is 3 times 10 to the 8th, okay? That is insanely fast, okay? However, nothing can beat the speed of light, right? This is a fun physics fact to know, is that the speed of light is the universal speed limit. Nothing will ever go faster than the speed of light. Nothing that has mass can ever exceed the speed of light. So why is the proton able to have that high of an acceleration? Also, why can we ignore gravity? Well, first off, we can ignore gravity because g is really, really small compared to the electric field acceleration of 1.2 times 10 to the 10th meters per second squared, right? If you're comparing something that's like 9.8 or 10 to 1.2 times 10 to the 10th, it's almost negligible at that point. It doesn't even matter, okay? And why can acceleration be greater than the speed of light? Well, if we use v equals at, and t is less than 1 second, okay, then acceleration can be over 3 times 10 to the 8th meters per second, okay? Meters per second squared, okay? So, again, like I said, we're accelerating over this time in 1 times 10 to the negative fifth second. So the speed when it hits the plate is not going to be the speed of light. It can't be. Physically speaking, it can't be, okay? And then figure out the electric field strength between the plates. Well, the easiest thing to do here is just use Newton's second law, right? F equals ma, okay? But you also know that the net force is equal to the electric force equal to the electric force on the particle. Well, what's the formula for electric force? QE. Easiest way to do it, okay? So set MA equal to QE and plug in everything we've been given, okay? This is a proton, and it gives us that the mass here is 5/3 times 10 to the negative 27th, okay? So we should do 5/3 times 10 to the negative 27. Acceleration we are given to be, or we had solved as being 1.2 times 10 to the 10th, okay? And then Q is the elementary charge, because this is a proton, okay? So it would just be 1.6 times 10 to the negative 19. And then E is what we're trying to solve for, okay? So you would just divide the elementary charge on both sides, okay? You'd end up getting E equals 5/3 times 10 to the negative 27 times 1.2 times 10 to the 10th over 1.6 times 10 to the negative 19, okay? And that should end up giving you about 125 newtons per coulomb. You're like, whoa, those are huge numbers. How do we end up getting such a small number? Well, it's because when these notes are written, they're intentionally supposed to give you nice, clean numbers, okay? Okay, projectile motion example. All right, throw back to physics 1, right? You remember when you were younger and cooler back then? All right, have fun.